Well, of course, the smaller step size is going to get you a more accurate answer, and that should minimize the absolute error, the relative error, and the percent error, as our example illustrated here. But what if we want a little more accuracy? Well, suppose function f can be differentiated n plus 1 times, and at each point in an interval containing an nth order Taylor polynomial, with f with center a, is, here's the Taylor polynomial, f of a, f prime of a times x minus a. You remember doing this in Calc 2. f2 primes over 2 factorial times x minus a squared, etc. Finally, the nth derivative evaluated at a over n factorial times x minus a to the n. That is the nth order Taylor polynomial, and all derivatives up to the nth derivative agree with the function at that point. So, and you might also remember for each x in the interval between, it would be between a and x. Now there's at least one point between a and x such that the remainder is f of x minus some p n of x, the error in approximating the function with the Taylor polynomial, and that would be n plus first derivative evaluated at c over n plus 1 factorial times x minus a to the n plus 1. This tells us that we can express the function f as f of x equals f of a, f prime of a times x minus a, f2 primes of a over 2 factorial times x minus a squared, etc. I think you can follow that all right. And this to here is called the Taylor formula, and if I add this, that's the Taylor formula with remainder. And so Euler's formula can be written as y at n plus 1 is y of xn plus y prime of xn times xn minus 1 times x sub n plus 1 minus x sub n, and is therefore, look, first degree Taylor polynomial. Then by Taylor's theorem with remainder, we expect an error involved in approximating the function y of x with y of x sub n plus 1 is y of xn plus y prime xn, and there will be a Taylor remainder, and here's the Taylor remainder, y double prime x h squared over 2 equals y double prime of c times h squared over 2 for c between some number between x sub n and x sub n plus 1. We don't know what the value of c is, but we can always pick the maximum of the derivatives, second derivatives actually, of y at x, for x between xn minus 1 and xn, and then we'll know the local truncation error will be proportional to m of h squared over 2 at each step. So the local truncation error is proportional to the square of the step size. So that says order of error is square of the step size. So the error in using Euler's formula to approximate the value of a function is on the order of h squared. If we were to half the step size, then the error would be reduced by a factor of 1/4. Since h over 2 squared is h squared over 4, it can be shown that the global truncation error is of order O of h times, h to the m minus 1, whenever the local truncation error is order of h to the m. So in other words, we drop a factor when we go to the global truncation error. I confess I'm getting a little tired, so I want to make some more videos later.
Poor baby.